All right, so today we're going to do some streaming stuff again. We haven't done that in a little while. And we're going to look at two problems. Well, actually, one's a special case of the second. We'll look at distinct elements problem and then slightly more generally, uh, moment estimation, focusing on the second moment. I'll explain that. To recap, what have we been up to? We did linear expectation in that first lecture was kind of your usual warm-up examples. We did heavy hitters in our second lecture. We did linear probing after that. You got to see some fancier hash functions. Then we did that random contraction algorithm for minimum cut. We did random graphs and giant component. That was our introduction to concentration of measure. Concentration of measure will come up again today. We did some randomized rounding for linear programs, some approximation stuff. And then last time we did some online algorithms. We did caching and we did BioRent, most of BioRent. Yeah. All right, so today, so we're going to be looking at these two problems, distinct elements and the second moment, estimating the second moment. I'll explain that in a moment. Actually, we won't be doing this. But we'll be using variance for, I think, the first time so far in the class, which is kind of funny. And also thinking about ideas for reducing variance. But we'll cross that bridge when we get there. Okay, so has anyone used Google Analytics before? Okay, you have a sense of what it does? What's it useful for? Okay, so Google Analytics, like you have like some kind of like website, right? And people use your website, of course, but you want to learn something about who's using it, right? So like what would you want to know about your website or the use of your website? What's probably the one thing you want to know? Yeah, demographic. Uh, sure. Even more basic though. What's the first thing you want to know? Huh? Is it what? Oh, if it's running. Okay, that's true. And that was an issue for me this week. Okay, second thing after whether or not it's crashed. Yeah. How long? What? Oh, I suppose that's not a bad. Yeah, okay. How long someone spends on your site? Still not what I had in mind. Okay, how many people visit the website? Yeah. But in particular, you don't want to just know like how many times, you could have just counted on your server how many times it was called and just had a counter. Yeah, how many distinct people visited your site? Uh, because if you actually look at your log, you're going to find that search engines are going to your website like 99% of the time, and most of the time, no one's actually interested in your website. At least that was my experience. So what you want to know is how many different, besides just web crawlers, are using your website. Okay, so that's one of the things that Google Analytics will do. It's maybe their most popular feature. Here's a blog post I found on Google. Where they talked about how they identify unique users. And one thing kind of interesting was they said in 2017, they actually started updating how they calculated things to try to get more efficiently count users with higher accuracy and lower error rate, typically less than 2%. Okay, so that's already like kind of interesting. Just words like more efficiently. Somehow they're doing something non-trivial with room for improvement. High accuracy and low error, right? So they're not trying to do things perfectly. Right? That's kind of interesting. And so something happened in that 2017 range. And so I looked for articles coming from Google around that time. And so around that time, they put out a paper called Hyperlog in Practice, engineering an algorithm. And Hyperlog is a well-known algorithm for this distinct elements problem. Okay, so this is something that that people work on. Okay, the basic model is going to look a lot like heavy hitters. Okay, so we're going to be working in a streaming model. So you have lots of elements coming in. In principle, there's way more elements in the stream. There's way more different possible elements that can fit in your computer. Okay, so you are this small, modest computer going through this stream. Okay, and our goals are going to estimate the number of distinct elements that pass through your computer. Okay. So notation-wise, I'll use M M as in mom, for like total number of elements in the stream. N will be the number of like the universe of from possible elements. So it'll be from 1 to n. Okay. And to just make life easier, I'm going to assume they're kind of within a polynomial factor of each other. So if something works as like 1 over poly n, that's same as 1 over poly m, and we can easily take certain union bounds. Okay, just to keep things simple. Okay, now distinct elements is a special case of moment estimation. Okay, so in general, for each element I, there's some frequency of how many times it appeared in the string. Okay, and the kth moment is defined as the sum over all the elements of that frequency taken to the kth power. Okay, so in particular, the 0th moment, where you're raising everything to the 0, where 0 to the 0 counts as 0, 1 to the 0 counts as 1, 10 to the 0 counts as 1. That'll count the number of distinct elements. Okay? The first moment is not too okay. The first moment is not too interesting. It's just counting up the total length of the stream, of course. That's pretty easy. The second moment is summing the squares of frequencies, and apparently it's quite useful. One of the names that I've seen given to it is called the repeat rate. Okay, and I read that it's useful for computing something called a surprise index from statistics. In general, the kth moment for k greater than or equal to 2, they're going to reflect how skewed the data is. Yeah, because if you want that kth moment to be big, that's when the data is really sitting on one coordinate, out of m. Okay. So if you can estimate f sub 2 or f sub 4, the higher moments, you're going to get some sense of kind of how evenly distributed your data is. So I've seen that if you're like some database person, kind of doing data partitioning and stuff, you might choose a different strategy depending on kind of how lopsided your data is distributed. Okay. All right, so that's the interest in moments. We're going to just do F0 and F2 today. And there's a very famous algorithm for F sub k due to Alon Matthias Ligeti that's left as an exercise in the notes, although it's pretty tough. Okay, we're going to do F0, F2. Those are fine. Okay, and F0 is actually going to be a new algorithm. So this is sort of a new lecture, and we'll see how it goes. I mean, relatively new. It came out a couple years ago. All right, so we want to estimate the number of distinct elements in the stream. And before I take you in a particular direction, I thought I would solicit suggestions. Any ideas? The hard part, of course, is you can't write down the name of everything you've seen so far. Yeah. The what? The good Turing? No, you might know the name of something that I don't know. Okay, well, you, did anyone recognize it? What was it? What did you think the name was? Oh, good Turing. Oh, Turing did do. Paul might know. Ah, okay. I can think of a way to try to implement this, but do you remember how it might have been implemented? Anyone? Yeah. Oh, you could do some heavy hitter thing? Okay. Okay. So you wanted to do some stuff. So in our heavy hitters algorithm, we created all these counters. We created a modest number of counters. In one instance, you had like 1 over epsilon counters and everything kind of hashed down. And our guarantee was that every error, with high probability is going to have like epsilon times m additive error, right? Epsilon m error. If I repeat this enough and you remember all that. So, okay, maybe you want to use this, and if an element comes in, I could check its counter to see if it's non-zero. The only tricky part is that our guarantee might return non-zero for everyone. I mean, because there's some additive error. of epsilon m. So I think, at least on the face of it, yeah. You just did not thing we did on Tuesday and then talk how many times the cache gets like missed. Oh, okay. So okay. So on Tuesday we did randomized caching. We did this kind of 1-bit LRU, or not recently used caching, and you want to see how often somehow study that algorithm. Well, okay. So for that, I would be a little bit careful in the sense that, for instance, I can imagine filling up the cache with the first k distinct elements. The next k flushes it out. And now the next set of k elements, it feels like on one hand, it could be brand new, and then your cache does something, or it could have come from that first group. Your cache would do the same thing. But if it came from the first group, it shouldn't count as another distinct element. These are fun ideas. Yeah. Something like a Bloom filter. Okay, so Bloom filters we haven't discussed, but idea is to make a very large bit string, okay? And each key gets mapped into multiple bits, and you set that to be 1, okay? And then to check if something exists, you check to see if all, 3 or however many locations you choose are set to be 1. So you're hoping that the multiple hashes you're less likely, because you need many collisions, right, to get a false positive. You might have studied Bloom filters in a class before. Do you remember, like, if you have, L keys roughly the size of the Bloom filter to get some reasonable probability, if I remember correctly? So I'm pretty sure with L keys, you're going to need something like L-ish bits, okay, 5L or something. But you do get in practice some nice winnings because you're using bits instead of bytes or words. Okay? But you still need something proportional to the number of keys to get a decent thing. Okay. Yeah. Okay. So here's what we'll end up. Okay. Well, here's a warm up. Okay. So suppose I gave you the following subroutine, and later we're going to figure out how to implement this. Okay. Suppose I told you that you could sample for any fixed probability you want to choose. Okay. Every distinct element was probability p. That's non-trivial to do because you want to make sure you don't resample an element when it repeats or something, right? But assume that we'll figure that out later. Okay. And so you just have this kind of streaming algorithm that does this nice thing for you. As the stream comes in, it's maintaining a random sample where every distinct element so far is sampled with independently as probability p. And you get to choose p. That's your parameter. Does that inspire any ideas? You can make p equals 1. You take all the elements, of course. Okay. But now you're also holding all of b on your computer. So b starts to get very big. So assume okay, you do have this nice algorithm, but you still pay for the size of b in your space. Yeah. There's a still estimation if you take like small probabilities and then like if you see a new one that you can do some statistical. Okay, let's do some statistical stuff. So let's just figure out what's the expected value of b for some fixed p. Well, how many elements should be in b? Well, why f0? Oh, what's the expected number of elements in b? F0 is the total number of distinct elements. Yeah, p times f0. Okay, every distinct element gets sampled as probability p. So for whatever probability p, just returning size of b divided by p, kind of like undoing the sample, will give you an unbiased estimator for a number of distinct elements. Okay, nothing too deep there. Okay, so that's at least an idea. Now, okay, so now the question is, what should p be? Like, suppose you sort of knew f0. Of course, you don't because you're trying to get it. But like, pretend, trying to figure out the ideal p relative to f0. What would we want p to be? Or another question is, what are the trade-offs of making p big or p small? Yeah. Okay, so if p is big, there's gonna be less standard deviation because yeah. So in particular, what quantity gets bigger as p gets bigger? Well, this one here, the expected value, right? And we kind of know that for larger mean, things are going to be better behaved. Okay, but then what's the downside? Yeah. Oh. No, you have some like data structure that's maintaining the set for you. Think of it like that. And then we'll figure out how to implement that later. Yep. You just have a set. At a certain point, so somewhere in the stream, you have the set B, and that set B is a sample based on the elements seen so far. Yeah, nothing too magical. Right. Okay, so someone said base. Okay. So, right. So if we remember this concentration phenomena, right? When we have a bunch of independent random variables and they're bounded, right? Their sum is going to be concentrated around the mean, and the probability deviation goes down exponentially in the mean. Yeah, the more precise bound was something like this. The odds of being off by epsilon, e to the negative epsilon squared times mu. Okay? The important thing is the mu. Okay, so our set B, we can think of it as a random sum, right? Where you have an indicator variable for each of the distinct elements. Okay? So we can apply this thing. And now we start to get something like the probability of, say, being an epsilon fraction bigger than your expectation is, bounded above by. Hold on, just plugging in. Yeah. Yeah, so something exponentially small in PF0. Okay, same for the probability of being smaller than the average. Okay, so fine. Okay, so if I want this probability to be 1 over n squared, 1 over n to 10, okay, something sufficiently small, so I kind of don't have to worry about it. What do I need PF0 to be? Log n? Log n over epsilon squared, I heard in the back. Okay, right? That's just to cancel out terms. Okay, so, all right, so ideally, we would like to be able to choose P so that PF0 is roughly log n over epsilon squared. Okay, maybe it's between C log n over epsilon squared and C over 2 log n over epsilon squared for a sufficiently large constant C. Okay, so of course, this is not an algorithm yet. You don't know F0 ahead of time, and we also haven't implemented B. Okay, but we're just kind of building some ideas. Okay, good. All right, so I think this presents kind of two obvious questions, right? If you wanted to do a strategy like this. First question is, how would you implement B in a stream if I just gave you a particular P? Okay, how can you do some kind of sampling the distinct elements in a stream? And the second question is, how can we basically kind of guess a reasonably good value of p? We do have some margin of error, but the trick is that we don't know f0 ahead of time. Seems like the strategy needs f0 for it to work. Okay. Those two questions make sense? Okay, this will be fun. All right, let's start with question 1. I give you a fixed p. Okay. How can we sample every element, distinct element with probability p? The eventual algorithm will not be super complicated, so you might be able to guess it. Yeah. So like maybe just said that every time you see an element, put it in E with probability P if it's R dot set already. Okay. Okay, so here's maybe like a natural start, right? So maybe you start with an empty set B, and for every element EI, okay, so should I write if EI is not in B? Okay. If that element you haven't sampled it yet, then with probability P, add EI to B. That certainly seems like what you should do on the first iteration, right? First element comes in, you basically have to sample its probability P. Okay. What if EI is in B? Just skip this element? Okay, so then this is the whole code. I guess. You'll have to add, if you don't add it to B, you have to add it to like a not B set. So, oh, well, if you want to start adding an EI to not B, then that's going to start taking a lot of space. Yeah. Remove it with like some probability 1 minus D or something. Okay. Okay, so if EI is already in B, then with probability P, maybe 1 minus P, remove it, question mark. Yeah, something like this. But what's the intuition? Okay, so I guess the issue is like, what happens when an element appears twice, the second time? Okay, it seems a little bit tricky, right? Okay, so if you didn't sample it the first time, and you sampled it, sorry, uh, right, okay, good. Now, for example, okay, so let's just say that the first element appears twice in a row and walk through what happens, right? Okay, so with probability P, okay, so on one possibility with probability P, you take it. It's probably 1 minus P, you don't take it or something, right? So this is in B, not in B. And now, what do we have here? So you're saying if it's already in B, then with probability 1 minus P, we remove it. With probability 1 minus P, it goes over here. With probability P, it goes here. And in here, P 1 minus P. Okay. So overall, what's the probability that we keep it? P. It seems to come out to P. So we have P squared plus P times 1 minus P. You get P times P plus 1 minus P, so you get P. Okay, so I think that's actually what we want. Here is another way to, I think, express it. Okay. As the elements come in, if I've already sampled, there's just another way to look at it maybe. If it's already in a buffer, I'm just going to remove it. Just remove it no matter what. And then if with probability P, I'll add it to B. Okay. This way you actually don't have to do any calculations like last time. What's the idea? Why does it work? Intuitively, what's it doing? Yeah.
It's removing it, and we're kind of just it's like equivalent to working with a set of distinct elements.
Yeah, you could think of B as always sampling the last instance of each element appearing in the stream because it just throws out, if you had to take it, I'll just throw it out. Okay, so it's very cute. Yeah, this way you can sample the last instance of every element as it appears in the stream. Okay, cool. That's fun. Okay, so now we know how to actually implement such a set B, but we don't know kind of how to figure out the right probability P. Hey, we kind of have a sense of what it should be. We like it to sort of be like, roughly inversely proportional to F0, allowing also for some log n over epsilon squared. Okay. All right, so now there's sort of a question of like, how can we sort of intuit P? Yeah. Yeah, okay. Yeah, so let's go slow. So you want to stop the algorithm at powers of two? Okay, so maybe initially, what do we start with? Okay. Now I do want to try to do some pass through the stream, but okay, we'll start with p equals 1. Okay, so for example, you could start counting basically f0 initially when you set p equals 1. Okay, so can we try to lower and adaptively change p along the way? Can we do maybe sort of like a chicken egg and egg kind of thing? Right? We kind of like initially you just count things deterministically, and then you have an estimate f0 that lets you decrease p a little bit. And that'll also help you keep estimating f0 until f0 got big enough you can justify decreasing p again. Something like this. Okay. Okay, I think we might end up doing something like this, but it gets a little bit tricky to analyze because at some level, one algorithm's errors may depend a little bit on a little error coming in from, you start estimating f0 and then you start making more decisions based on your estimate. And f0, if you're at this, your thing was a little bit off before, does that kind of propagate? You see what I'm saying? Okay. Here's maybe a lazy way to try to do it first. Okay. And we'll eventually come to an algorithm that looks like what we just discussed. Okay. Suppose you just kind of try to run everything in parallel for all these different values of p. So I have b0 will sample, will take everything. b1 will sample everything with probability 1/2. Okay. b3 will sample everything with probability 1/4. So b10 will sample everything with probability 1/2 to the 10. All right. So you can imagine running all these things in parallel. Okay. But an obvious problem is maybe I can think of two questions, right? What happens when some of the BIs get big, right? B0, you're just taking everyone right away. And then two, at some level, like which BI do you want to use to actually estimate? Because right now you're running all these in parallel, right? So now you just have log n copies of B. Each element comes in, you do the same thing for each copy. All right. Maybe question one, it may be more intuitive. At some level, just to satisfy my space constraints, once B0 has, a lot of elements, I got to do something with it. Yeah. Throw it away. And I guess that leaves us with B1, B2, B3. Why should I feel safe throwing away B0? Yeah. Oh, either one. Okay, if B0 is big, F0 is big. So probably 1/2 should be okay. Right? And now when B1 gets too big, B1 should be F0 over 2. So once B1 starts getting big, F0 may be big enough to justify set B2. Now sampling is probably 1/4. Yeah. Yeah, here we do, just to make things simple. So you only need to go up to log n. Okay. All right, that's at least intuitive, right? So let's figure out how to actually prove this thing can work. Okay, so let's look at some threshold like log n over epsilon squared times a big enough constant. Okay, but at some level, if my expected value is, I don't know, this threshold over 4, then with very high probability, the estimate's going to be good. Okay, so here's we should have a absolute value around this. Okay, the size of bi, the size of bi minus its expectation. The odds of it being off by more than epsilon fraction of its mean. That means it's off by more than 1% error, 2% error. It should be 1 over, say, polynomial in n. Okay, something small enough that we can just union bound over, say, the length of the string. Okay, so fix this threshold so that once your mean is bigger than that threshold, if I put e to the negative tau over 4, I'll get 1 over poly n. Okay, for a conveniently large polynomial. Okay, so we'll start there. Now, okay, so that's big enough, and so we can kind of assume that's always the case. Whenever, at any point in the stream for each I, if pi times f0 is bigger than tau over 4, I can basically trust the estimate given by bi. Okay, so as long as, even if I don't know f0, because the algorithm's oblivious to f0 actually is. Okay, if at that point in the stream, if it kind of looks good, it will be good. Okay, now suppose bi has more than tau elements. Okay, so what do we kind of know? At some level, we know that it's already bigger than, that probably is already bigger than necessary, because I really only need to get the tau over 4 to get a reliable estimate. Okay, that also means that if I went down by a factor of 2, okay, pi plus 1 will be big enough. Okay, so if my set gets, bigger than this threshold, some of that probability is too big, and one factor of 2 less is big enough. We just kind of put that in and go about it carefully. Yeah. Oh, no question? Makes sense. So at this point, we can discard BI. Okay. Now, imagine I did one more thing. Imagine I also kind of correlated the BIs. Okay, so that if BI takes something, then BI minus 1 always took something. One way to do this is for every element, when the 10th element comes in, I can draw a random value theta uniformly between 0 and 1. Okay, and I'll say that, okay, if this value is less than pi, then I'll add it to bi. Okay, so if I draw like 0.1, it'll of course go in b0. It's less than 1/2, so it'll go in b1. It's less than 1/4, so it'll go in b2. It's less than 1/8, so it'll go in b3. If it's less than 1/16, no, so it won't go into b4. Okay, so in that way you can like completely correlate this, but you still have the same probabilities. Okay, that'll make it easier to interpret this sort of slick version of the algorithm, which comes back to the original suggestion. Okay, so I'll start with an empty buffer or set and probability 1. So as elements come in, I'm going to add it to my set B with whatever p is, probability p. Okay, and then so this is like the same as sort of just a sampler from before. Okay, but every once in a while, every once in a while, you'll hit your size threshold. Okay, all right, so your buffer size becomes at least tau. that sort of buffer for when things are plenty big. Okay. All right. So there's two hidden steps behind white squares. You might be able to guess. Yeah. Uh-huh. And half p. Okay. So we're gonna half p, and we'll drop every element independently with probability 1/2. Okay. You can think of that as implicitly just shifting down from 1b0 to b1 to b2. Okay. So what you're left with is like a relatively clean algorithm. Okay. You put that all together, you're now approximating distinct elements up to, some epsilon error in log n over epsilon squared space. You're holding that many IDs. Yeah. Yeah, exactly. Yeah. That gets us to p over 2. And pretty neat, right? This is like a relatively new algorithm. Only came out a few. The previous algorithm was way more complicated. It used to take me like a whole lecture to do this, and you need like k-wise independent hash functions and all this stuff. Okay. Any questions? Yeah. You assume what? I'm not trying to okay, so the question is, are we assuming we know n in advance, and are we trying to estimate n? So n was sort of the space from which the elements could come from, and f0 is a subset of n. Yeah. I think you can at least get this to log m because only m different elements will appear and stuff, but yeah. Also in this algorithm, like this b log n is not so significant after all, because you kind of naturally go down. Yeah. Oh, I don't know. I think we only needed it to be. I mean, I didn't try to be tight, but we just need e to the negative epsilon squared tau over 4 divided by maybe 2 to be 1 over poly n. So maybe 16. Yeah. There's more slick ways to go about this, but I was trying to keep it simple. All right. Yeah. Oh, okay. So I want to be able to uh it would be nice to be able to say all throughout the stream this applies. And so we can union bound it. Yeah, so this one union bound over the length of the stream. Yeah, otherwise we could have done like log m instead of log n. Yeah. All right, we're making good time. Okay, so let's do part 2. We're ahead of schedule. Yeah. Any other questions for distinct elements? All right. Okay, so F2, from that moment defining slide from before, we're now looking at the sum of frequency squared. All right. So, okay, sounds good. So I guess we have the usual thing. We're going to be doing this in a streaming model. Okay. And same as always, does anyone have any ideas you want to suggest? So I'm just trying to estimate this quantity, the sum of squares for all the frequencies this time. Yeah. Okay, can you use heavy hitters? Are they going to be the more important ones here? Okay. Uh, it's an idea. Okay. I mean, I think that there's one concern that comes up like before. So you can report something like I equals 1 to n, your estimate, I'll write fi tilde for the estimate from heavy hitters, and you're only guaranteed things like f sub I plus epsilon m squared. And I'm starting to worry about the epsilon m squaring getting really bad. Yeah.
You're like trying to sample every pair of equal elements. It's the problem.
Can you sample every pair of equal okay, with some probability. So can you help me understand what it is?
They essentially like the higher elements is the J.
So these are indices in a stream. Okay, so somehow try to sample repeating pairs. Okay, and how how can we use that? That's an interesting idea.
It's like if I'm gonna pairs like Fi times like number of repeating pairs like Fi choose two.
Oh, okay, okay. So okay. So at some level, if we were trying to estimate something like, this is kind of a cute idea. Okay. Um, Fi choose two, something like this. Or I guess it can just be Fi square, yeah, something like this. Then we can try to sample two distinct indices that correspond to the same element. And if we can estimate the number of distinct pairs like this, that would be good. And that would get you close. And maybe it wouldn't be that hard to take something that worked for the sum of Fi choose two and do Fi squared, because that just allows for switching them and also same indices. Yeah.
F sub two equals like the squaring of F sub one minus the like cross products.
Oh, okay. Uh, F sub two is equal to at some level like F1 squared. This is terrible. If I took something like F1 squared, then I'm going to get all these Fi squares plus all these two Fi Fj terms, the cross terms. And if you could kind of estimate the cross terms, yeah. But I think that's going to be, yeah, I guess maybe one way, yeah. I don't know if that's going to be any easier to look at. I mean, clearly, since F1 is easy, if you can estimate F1 in the cross terms, you get F2, you can do F2 and F1, and you get cross terms. There might be some issue because of approximations, uh, but I guess maybe to that, I don't know if IJ cross terms are going to be any easier. Feels like more, yeah,
So similar to the choose two quantity.
yeah.
I guess like you can use what you used before to kind of not up like every time you see a distinct element, then every time like remove it, you just like add plus like two and then plus three and so forth, and that consecutive sum gets you close.
Okay, so yeah, in particular, okay. So first, okay, so this idea, which is actually kind of cool. Um, if you can do this, then you can recover this because it's going to be like 2 times this plus the n for the diagonal or something, right? Or maybe this plus distinct elements. Um, okay. Now, okay, at some level, I think you're getting into the implementation of this possible approach. Can we take that previous algorithm and like kind of keep track when we are sampling and notice something appears again? Okay, now one of my concerns, at least from before, is that we had this pretty small set B that's sampling a small number of elements distinctly. And so when an element repeats, you're really hoping that one of the previous ones is still in your set, but your set is only keeping a very small subset out of all the distinct elements. I mean, I haven't really thought this through, but if I kind of roll through all the elements once and roll through the elements again, at the second pass, it's going to find almost nobody from the first pass. You're only going to get log n over epsilon squared hits. Yeah. It's a cute idea. I don't know how to do it at the moment, but yeah, maybe it can be extra credit homework. Okay, any other fun ideas? Okay, so we're gonna do something based on hashing this time. It's not gonna be as cute in some ways as before. Okay, okay, but it's gonna be based on randomly signed sums. Okay, so I'm going to start with these four y's independent. I mean, you can think of this as just ideal hash functions, and then afterwards figure out how much independence we needed. Okay, but for every element, it's going to assign a plus or minus one. Okay, plus one, minus one, plus one, minus one. Okay, and directly, all we're going to track is the sum of frequencies times their sign. Okay, which if you're doing in a streaming fashion means element 5 comes in, you compute the sign h of 5. If it's plus 1, I just add 1 to my sum. If h of 5 is minus 1, I'll subtract 1 from my sum. And then at the end, your sum will give you this sum of these plus or minus 1s times frequencies, where the signs are sort of random. Yeah.
Is the sum of the fi squares equal to the repeat rate? Like, how do we define them?
Oh, it's just a name. The sum of fi, I just read in a paper that the sum of fi squared is called the repeat rate. Yeah, I don't really actually know. I think it was also called that by statisticians. Yeah, just to make it look fancy. Okay. All right. So the algorithm itself is sort of like dead simple, right? We're just keeping a tally of random plus or minus ones. Okay, which at the end, when you look back, element I, it appeared 10 times, its sign was minus one, so you get minus 10 in the overall sum. Next element appeared 15 times, sign was plus one, it adds 15 to the total sum. Okay, and the estimate is going to be the sum squared. The algorithm makes sense? Okay. Does anyone see why y squared is not a crazy estimate? It doesn't seem a priori to be, or anyone see the intuition?
Oh, because all the cross terms have expected value of 0.
Okay, so let's go slowly, right? We're going to be summing up all this like h1, f1 plus h2, f2 plus hn, fn, and all that's going to be squared, right? And as we previously discussed, somehow if I just took all the f's and summed them and squared them, I would get all those powers of 2 that I wanted plus those cross terms. Okay, so let's see what this does to the cross terms. So we're going to get, well, I'll put it inside. We'll take linear expectation in a moment. Hi squared fi squared plus 2 times the sum. These are just the cross terms. And j is I plus 1 to n hi hj fi fj. Okay. Now with linear expectation, we can look at each of these terms apart. So let's look at the first type, expected value of h squared I. You can even pull out the fi squared. Okay. What does this equal? Fi squared, the expected value was 1 because it's a random sign. Minus 1 squared is 1, 1 squared is 1. Okay. Now if I look at one of these cross terms, what do we get? Because formally we need to do one thing here. Yeah, so how does 4y's independence play in? Okay. Yeah, on first pass, we can just, it might be easier just to think of them being completely independent. And afterwards, we'll figure out how much independence we needed. Okay. But because they're independent up to pairs, or including pairs, I can separate the two. And the expected value of hi is 0, right? It's 1/2 the time, -1/2 the time, you get 0. Okay. So in that way, all the cross terms disappear, and all you're left with is the sum of fi squared. Okay, good. So that very simple thing actually does give you an estimate, an unbiased estimate of f2. But what we're really interested in is kind of how often is it going to be like a good estimate, right? We want to get to that like 1 plus or minus epsilon kind of thing. Oh, how often can I get it within 10% error? Right now, it is okay in expectation. Okay, so that brings us to the variance portion of the of the lecture. Okay, so presumably many of you have seen this before. Okay, but let's just parse this. Okay, so the variance of a random variable x. Okay, let's look inside the outer expectation first. I have the random variable x minus its expectation, right? So how much is deviating from its average value? Now, if there was no squared there, you just get 0 because it'll go bigger and it'll get smaller, right? So we're going to square it as sort of like a proxy almost for the absolute value. Okay, so sort of like the expected error squared in some ways, if you think of a deviation from the mean as some kind of error. Okay? And it's not so hard to work out. It's not as an exercise. You can rewrite it as the expected value of x squared minus, it sounds the same, the square of the expected value. Okay. All right. So why is this going to be useful to this question of kind of how close we are to what we want? So we're going to use something called Chebyshev's inequality. Okay. So saying, okay, how much, how often is the absolute error or deviation in our application still be like an error? Okay. At least some value alpha. It says at most variance of x over alpha squared or something. Okay. Something proportional to variance. Okay. But how do we prove this? It's actually not so hard to prove. Okay. I'll do the first step. I'm going to just square both sides. Uh, okay. I just squared both sides. Okay. I want to get to that on the right-hand side. Any ideas? It's a trick you've seen before. Yeah. Okay, we're going to use Markov's inequality. So in the numerator, we're going to get the expected value of the thing we're bounding. I think it's important to point out that by squaring, actually, it was already the case with absolute value, the variable is non-negative. Okay. Something like this. And then what's the numerator? Numerator the variance. Okay. So it's actually just, Markov plus plus. It's not such a big deal. All right, but let's see what it means for us. Well, first we have to calculate the variance. It's going to get a little bit messier. Okay. So I'm going to appeal to that other identity for the variance, since we've already computed the expected value and we can square it. So now we got to do this y to the fourth. Okay. All right, so we have this big sum and it's a big polynomial and we're taking it to the fourth power. And if I apply linear of expectation on your behalf, we'll get this thing. hi, hj, hk, hl, fi, fj, fk, fl, right? Okay, so clearly we're in the world of hurt. Yeah, but these are all the, whatever, 4 of them. quartets. All right. So let's look at each of these almost on a case by case basis, right? So there's kind of like different ways that the HI, HJ, HK, HL can be distributed because they might be the same. I might be equal to J, K might be equal to L. Maybe they're all the same. Maybe they're all distinct. Okay. So we're going to look at each of those separately. So for example, what if they're all? What if they're all distinct? So assume in the following JKL, IJKL are always distinct. Okay. Okay, 0 because
regardless of what HI
yeah, that's one way to look at it. In general, because of 4y's independence, we can take these apart. Okay. You actually have 4 zeros in there. Okay. So what about the next one? HI squared, HJ, HL. So we can take this apart as well. And the first term is not 0, but those last two terms are. Okay, so you're getting 0 again. And the last one, same kind of story. Okay. These are both 0. Okay. What in particular makes these things 0? Sorry? Yeah, well, okay. Beyond 4, besides 4, what? Okay, well, here's some examples. Here's some slightly different behaving examples. All right, what about the first one here? HI squared, HJ squared. 1, because when I break this down, yeah, you can also do it on the inside. Okay. But you always get 1. Okay. What about this here? It's also going to be equal to 1. Okay. So what was the difference? Yeah, we had these odd degrees up here. And when it's all even degree, you get 1. Okay, so a single odd degree will go to 0. All even degree will get you 1. Okay. That's going to help us clean things up a lot. So if I go back to this monstrosity, all the more of a monster in my handwriting. Okay. So what's left? A lot of things will 0 out. Okay, so the 4th power, well, I'll write it out. I don't want to write it out. Okay. F sub I to the 4th, those are the 4th power. What's the coefficient? The coefficient is just 1, because there's only one way to get them all aligned. Okay. Yeah, so then now the distinct ones, and Fi squared, Fj squared, and what was the, or choose 2? Was this, because, out of IJKL, 2 of them are going to be equal to one value, 2 of them are going to be equal to the other. Okay. 4 choose 2 is equal to 6. I'll put that there. Okay, plus 6. Okay. Now, I want to relate this eventually to something related to F2 squared. That's my goal. Okay, just as a hint. So how can I take this, start making it look more like the second moment squared?
Why don't you just expand E twice root squared?
Why don't I expand, sorry?
You know how the variance is E y double minus that,
Yeah.
right?
Sure. Sure. Yeah, you could. Uh, we will eventually. I won't say much. Let's try to just work with this. Yeah. So, well, okay. How about this? If this thing was less than equal to something f2 squared, okay, how small can I make that blank?
Is this square on the outside or because we want it as big on the
3?
like on the outside.
Okay. Okay, so if you do f2, if you just did f2 squared, right, we'll get 2 times all these cross terms plus these powers of 4. Okay, but there's 6. So we want to scale it up by a factor of 3. That's either multiplying by 3 on the outside or square root of 3 on the inside. Okay, good. All right, sounds good. All right, now let's finally compute our variance. Variance of y2, expected value of y to the 4th, minus the expected value of y squared, squared. Okay, and what do we get? Maybe 3f2 squared minus f2 squared, 2f2 squared. Okay, so we're getting some variance proportional to the second moment squared. Something comparable to what we're going for, actually. Okay, good. Okay, so that's fine. Now, okay, so for some given parameter epsilon, right? I really want to know, like, okay, what are the odds that I'm off by, epsilon times my goal? What would Chebyshev's inequality give me? Sorry? Yeah, I think I got 2 because the variance has a 2f2 squared. Okay, so here I'm plugging in the variance, our 2f2 squared. This is our kind of right-hand side getting squared. The f2 squareds cancel out, and I get 2 over epsilon squared. Okay, so what does that say? That tells me that I can get like I can set epsilon to be like, say, 2. Okay, because epsilon to be 2, this will become 1/2. So with constant probability, my error is like 2 times f2. So I'm getting like a 3 approximation half the time. Okay. Okay, so we can get right now a constant factor approximation with constant probability with this one estimator. Okay. So now, any ideas for doing better? So I'm going to take this idea and I want to make it more accurate. Yeah.
Just do it like log n times of that. Take the average of the results.
Okay, we'll take the average, I guess here, log n times. Okay, so, all right. Here's what I want to focus in on. So at some level, okay, so this term here is the variance of our estimator. Okay, if I can just decrease the variance, then I'll decrease my probability, just completely proportional. Okay, so how can you decrease the variance in a word? Repeat and maybe 2 words. You repeat a bunch of things, and what are you going to do with the results? Average. Yeah. Okay, so we can average, right? So if I have some variable x with some particular variance, and I made some number of copies, and I took the average, okay? Then if you work out, the variance, you can pull out a 1 over L squared, okay? Some cross terms will disappear, okay? And you end up getting L times the variance divided by L squared, you get 1 over L variance. So if I took the average of 10 copies, I'll decrease the variance by a factor of 10. Okay. So, okay, so maybe coming back to here, if I want to get, for a given epsilon, I want to make the right-hand side at most 1/2 or something. How many copies will I want to average? Particularly, I want to deal with this epsilon squared term. If I take 10 copies, it's going to divide everything by 10. So I wanted to annihilate this 2 over epsilon squared. Maybe you want like 4 over epsilon squared copies or something proportional to 1 over epsilon squared. Okay, so here, right, just plugging in, you're going to get this 2 over L epsilon squared. So if you want that to be at most 1/2, you should be setting L to be, something proportional to 1 over epsilon squared. Okay, simple enough. Okay, so now, just by taking averages, okay, we can get kind of, arbitrarily good accuracy with constant probability. Okay, whatever the accuracy parameter you're paying 1 over epsilon squared now. Okay. Okay, so that'll give me a constant probability. Suppose I wanted to get probability 1 minus delta of it succeeding, so probability error delta, for some given parameter delta. Any ideas? So I want to take the right-hand side, in some sense, down to delta. Okay, so right now you can get constant probability of error. Suppose you want to get down to delta for some given delta. Okay, so one idea is if we set L to be, on the order of 1 over delta epsilon squared. Okay, as usual, my handwriting is terrible. Then this will start looking like start looking like delta. Okay, and you're making 1 over delta epsilon squared copies. Okay, that's just kind of plugging in, it goes down. Okay, but now what if I wanted to do something with high probability? So what if delta is 1 over poly n? Okay, I don't want to, right now we're saying, oh, we're going to have to make polynomially many copies. At that point, I might as well just remember all the IDs. Okay, so can we do, so that first idea was do a bigger average. And that seems like the most natural idea in the world. I'm asking you, can you do better than taking a massive average? You can repeat log 1 over delta time. Well, okay, now you're sitting with a lot of variables. What are you going to do with all of them? So it is true that we're going to want to find a clever way to take advantage of concentration phenomena, which I think is where the log 1 over delta suggestion is coming from. That's at some level what we need to do if we're going to be able to handle 1 over poly n probabilities. Okay, so I do want to somehow take advantage of the Chernoff bound. Okay, all right, so I set this up. Okay, right now I know that if I take say 1 over epsilon squared and average, I'm going to be correct 3/4 of the time and wrong 1/4 of the time. Where right means I'm within epsilon error, wrong means I have more than epsilon error, epsilon relative error. Okay, so you know how to make something that's right 75% of the time and is wrong 25% of the time. I want to be right almost all the time, essentially all the time. Taking the mean of all more copies is not going to get you there. Taking the mean is not going to get you there. Yeah, no, the mode is never useful. What's the third option? The median. Okay, Let's try taking a median. I'm going to take the median, okay, of some like log 1 over delta or log n bundles. Each bundle is an average of 1 over epsilon-ish, squared-ish terms. Okay, we're taking a median. Okay. Why? Why is this going to get you probability error polynomially small in n, or probability of error delta?
Because the median is not biased.
No, median is not necessarily unbiased. It's not an issue of bias.
It's like for it to be wrong, at least half the terms that will be.
Ah, okay. So the median is wrong. I need half of them, at least half of them, to be wrong, right? Because if the median's like too big, that means like more than half were too small, or something. No, more than half were too big, right? And if the median's too small, then more than half were too small. But if less than half of them are wrong, you can't have either of those. Okay, very kind of simple trick. Okay, now you only expect a fourth of them to be wrong. Okay, and if you start ramping up, these are all independent trials. So you start getting something like, the odds of getting half of them wrong is going to start looking like something like e to the negative, q over 2 or something, right? Where q is the number of things I'm taking a median over. So we start setting that to be log n. Now you're down to polynomial small n. You set it to log 1 over delta, and now you're getting delta. Okay, up to some constant. Yeah, it's a nice trick. So clearly this is much more general than just this particular application. Okay, it'll come up on your homework, for example. Okay, timing is great. So all put together, okay, we're able to estimate F2. Yeah.
So if you wanted to do FA, would you replace the like complex numbers?
At least not the original. I was wondering about that, but yeah, but well, I haven't pushed that all the way through, but at least the approach I had in mind is not kind of generalizing the signs to complex numbers, to roots of unity. But it's in the homework, or not homework. It's there as an exercise, but it's a very famous out. It's very clever. Okay, but let me keep proceeding to conclusion. So okay, so now you're able to get this very good estimate for F2. There's very good space, log 1 over delta over epsilon squared. We're kind of used to this epsilon squared term. It keeps coming up. And sort of that key last idea was what's called this median of means, or the median trick. Okay, so first you have some estimator. In our case, it was unbiased, but the variance was a little high. So we couldn't argue that it ever really got very accurate enough. So we just took the mean enough times so that I can get an epsilon approximation with, I don't know, probability 3/4. Just barely good enough probability. And once we get that, then we can drive the error probability down exponentially by taking the median of however many copies. Okay, so this median of means. You can imagine, sort of a generic thing for any kind of this, when you have sort of this weak estimator to get you started. Okay, so by coincidence, I wanted to mention that like Paul is almost the world's expert on median of means in some sense. He works quite a lot on statistical estimations. So if you want to know more hardcore stuff about median of means, he happens to be in the back corner uh, today. So and median means plus plus in all these different ways. No, it's just a coincidence. Okay, that's all. I'll see you guys next week.